Hello, everybody. I'm looking at the LabFlow Kinetics of an Iodine Clock reaction lab right now, and I want to give you guys a few pointers for getting your provisional data for this. So the first thing I'm going to do is I'm going to say I'm completing this virtually. I'm going to hit next, and I start to get some data that they want me to fill in here. The first thing is going to be reading off this thermometer here, which is pretty straightforward. Just keep in mind, this middle guy here is 5 higher than 20 and 5 less than 30, which last I checked was 25, and that you should be giving it an extra digit. I mean, even if you see it as being exactly at 25, that is not 25 there, that is 25.0. I see this as being just under that line, so I'm going to call it 24.9. The next thing are these videos, and this is probably the trickier thing that I get a lot of questions about. The first thing is that we need to put this clock here, this is minutes here, and this is seconds. We need to put the value in here in seconds, meaning whatever value minutes I get, I'm going to multiply that by 60 and then add it to whatever seconds there are there. These videos, one of the key things I think people get really frustrated about is calling when the color starts to happen. Now, what LabFlow wants you to do is to choose the earliest point at which the color changes. So if you kind of scrub through this like I like to, because you're probably a cheater like me, I find where that color starts to change there right when it starts, like right about something like that. And this is going to be the value that I'm going to go ahead and put in here. So I would do 14 times 60. What is that? 600 and 840 plus 849 seconds would be a reasonable value to put in there. Now, I'm not going to go through the whole thing, but I'm just going to tell you that if LabFlow thinks that any of your values aren't reasonable, it's going to give you kind of a little cryptic message down here. It does tell you which one it wants you to change, but then it just dumps you back to go back through this cycle again. And it does still have the old value that you put in there. So just make sure that before you go to start entering that data again, because you need to change something, read very carefully the error that they're giving you, because you don't want to go changing stuff that was already correct. You really want to make sure that you're changing the one that they're having an issue with. After we have completed our virtual data collection, we're going to get this table here that has various volumes that were used to prepare the solutions in the videos. And then we're going to have this provisional data where we now have the reaction times that it took for these reactants to change color, as well as this data right here. The first table that we're going to be asked to complete is going to be this IC3 initial concentrations table. If we switch over here, we can see that it is the data inside of IC1 that we are going to need to do this. Basically, if we look across here, we can see that they have various different volumes of each one of these solutions that they added to these. If you add these up going left to right here, you're going to see that they kept the total volume in each one of these to 10 mils. So like 3 plus 3 is 6, 7, 8, 9, 10. And the same for like A4 here. We have 1, 5, 6, 7, 8, 9, 10. So to fill this out, all we really need to do is just use the dilution equation. So first we would sum up all the volumes of all the different components inside of the mixture. We just established that that's going to be 10 mils. And then to get the initial concentration of, say, the thiosulfate, what we're going to do is we're going to see what the concentration of the sodium thiosulfate stock was. That is right here. It was 0.00100 molar. We will, in the case of the very first solution, A1, we're going to see how much volume was in that solution of that sodium thiosulfate. So that was just 1 milliliter. And then we're going to divide that by the total volume that was in that solution. And we wind up coming up with 1.00 times 10 to the negative 4 molar. You'll then just repeat that through the rest of all of these various solutions. Obviously, you're going to be doing the same bits of math over and over again. I really recommend some sort of spreadsheet program or something like that to help you do this math so you're not just stuck there doing it over and over again. The next thing we're going to be faced with is to calculate the initial rates. And this can be a little confusing because this honestly is a pretty complicated reaction. It is a compound reaction with a lot of things going on. But if we look in the PDF, we can see that we can basically track this based on the change of the initial concentration of the thiosulfate. Basically, the color was not going to change until we had used up all of the initial concentration of the thiosulfate. And if we just look at the rate equation, we can see that the rate is going to equal 1/2 the concentration of the initial concentration of the thiosulfate divided by the amount of time that it took to see the change in color. So for instance, for A1 here, we would go back to the initial concentration of the thiosulfate for A1. We would plug that in for this term here. The change in time for A1 is going to be 845 seconds, and then we'll multiply that by 1/2. I did plug that in for A1 here, and then I wound up getting this value here. Note that we are in molarity per second. For this reaction here, we're going to have the exact same type of situation. We're going to have to go to A3 now. I still get the initial concentration of thiocyanate to be 1.00 times 10 to the negative 4 molar. Why is that the same? That's because if I look up here at my data, A3 also had 1 mil of the sodium thiocyanate, so it had the same concentration initially. I can then plug that into the rate equation just as I did the other ones. Note that this is organized left to right, so you're going to have 2 of them for the cold and 2 of them for the warm, and then you're going to calculate those initial rates. And also note that if we look at this, this is making sense to us. So the cold one took longer and the hot one went faster, so that means that the cold one's going to have a slower rate, the hot and warm one's going to have a faster rate. That's the kind of trend we would expect. Ultimately, you are going to wind up averaging these across here. The next bit that we're going to be faced with is to basically use our method of initial rates to calculate the rate orders. The data was set up in such a way that if we look at these ratios here, we can see that, oh, first I wanted to point out that this is how we're defining the rate loss. So we don't need to worry about this right now, but A is going to go with the iodide ion concentration. B is going to go with the bromate ion concentration, and C is going to go with the H plus the proton concentration there. And if we come back up here, for instance, we said A1, A2, A3 were all going to allow us to get to A. And we can see in our data that the Ki, the source of our iodide here, was varied amongst those, and the other reagents were kept constant in those ones. And that's why these are going to be the ones that wind up canceling in our rate equation, and we're actually going to be able to get at the A value here. Now, the way that we've done this largely in the class is just by inspection, but I did show you, so when I do rate 2 over rate 1, so I'm following the A2, A1 right here, this would be my rate ratio. The relevant concentration ratio, this guy right here is going to go right there, and it's relevant because that was the one that we varied for those experiments. And again, so we've been doing this by inspection, where I would just take this ratio, and then, they're usually whole numbers in a lot of our problems, and we're able to just say, oh, A is 1 or A is 2 or something like that. I did do a problem that explained this in the homework solution guides in my notes, but the PDF here kind of yada yadas this a little bit, so I want to get into this just a little bit. What I'm going to do is I'm going to take the natural log of this, so I got the natural log of that. I'm going to take the natural log of this, I got that right there. I'm going to use the property that these are both being raised to the same exponent to say that that is the same as taking the ratio first and then raising it to that exponent. I'm going to use one of the log rules here that says that I can move the exponent out and multiply it up front as a coefficient. So I get this. So now I have this is equal to this, which means that if I want to get at A, I need to divide this guy by this guy here. And that's what's going to get me my A value there. So they have you entering this ratio here as a quantity right here. They've got you entering this ratio right here as a quantity right there. They've got you entering the natural log. So this whole term in the numerator here, the natural log of that ratio right there. And they've got you entering the natural log of this ratio right here, right there. And then you're left to see that what you need to do is take this number divided by that number, and that will be an exponent here. And they want you to not round this value. They want you to keep it, within your sig figs as a decimal value there. And then you're going to repeat that the whole way down. Again, this is a good time to maybe bust out the spreadsheet. Make sure you keep it straight which ones you're doing for each one of these. And you're going to be able to fill in 3 values for A, 3 values for B, and 3 values for C. The next thing you're going to do is you're going to average those three A values here, average those three B values, average the three C values together, and then you're going to round those to an integer because we've been working with integer values for the rate orders. I mean, not everybody does that. There's plenty of reason to use fractional rate orders, but it's a little outside of the scope of this class. So we definitely want to have those as an integer. One of the next questions that you're going to face is going to be the units of the rate constant. We can see in this table that we already have our summary from, I believe this is section 4 in chapter 12. We can see that we had molarity per second, 1 over second, 1 over molarity per second. Your book doesn't go into this, but I just want to point out that this trend would continue if we had a third order reaction, which is not one that we've considered, but definitely a possibility. This trend would continue. So like to go from here to here, we divided by molarity. To go from here to here, we divided by molarity. So the one for the third order would be molarity squared times seconds. And if we did have a fourth order, which now we're just kind of getting silly, right? The unit for that would be 1 over molarity cubed times seconds. The next thing we're going to be faced with is to get the rate constants. And if we go back and consider the equation, the rate equation, this one right here, we now have a table with all of the rates. We have a table with all of these initial concentrations, and we know the orders at this point. So we're just going to work that equation backwards. To do all of these, where the K is just going to be the rate divided by all of their initial concentrations with their order values that we've established there. Make sure that you're using the whole value numbers for that. The next thing that we're going to need to do, we do have kind of a big part here that just kind of gets tacked on here at the end. You're going to go and get the average value for the rate constant K. That's just going to be for all of the room temperature ones. So you're going to average all of the rate constants in this table here and divide by, what is there, 7 of them there. And you're going to put that right there. And then you're going to average the rate constants for the cold water, which is one that we determined right here. We're going to average these two together. Put that in there, and you're going to do that for the warm water. That's the second line in this IC9 table here. And then you got your temperature values that you established. That's going to get propagated in there for you. And then we have the slope of the Arrhenius plot. So we need to make an Arrhenius plot. We're going to have to do that in something like Excel. These are the points that we're going to have. We're going to have 1 over the hot temperature that needs to be in Kelvin. So we were given that in degrees Celsius. My hot temperature is 44.8. I'm going to need to put that in Kelvin and then take the reciprocal of it. That'll be an X value. The natural log of the K for the hot, so that's going to be, I'm going to take the natural log of this value right here, the average rate constant for the warm water, and then I'm going to do that for the room temperature water, and I'm going to do that for the cold water. Remember, we're always in Kelvin for all of these. This is going to be our smallest X value, right? Because this has the largest temperature. I take 1 over the larger number. That's going to make it the smallest number. The K values you get should be fractions, I can't guarantee that. Your mileage may vary, but if they are fractions, then the natural logs are going to be negative. But the trend does continue because K is going to have the largest, because the hot is going to have the largest K. The natural log of that is also going to be the larger of the numbers. So you're going to have, 1 over TH is going to be furthest downfield here to the left on X, and ln KH should be the highest one up here. And we're going to get a plot that roughly looks like this. It may cross the x-axis here and become positive, though. That's perfectly reasonable as well, depending on our data. You are going to get a plot from that. You're going to do linear regression and get a equation of the line there. The slope of that equation is equal to negative EA over R. And this EA is the activation energy that we want. So the EA, therefore, if I rearrange this, is going to equal negative M times R. We're going to want R in the units of joules per mole Kelvin, so we're talking about 8.314. We're going to multiply that by M, which has units of Kelvin. You can kind of tell that if you look at the equation here a little bit, because it needs to be multiplied by X, which is 1 over Kelvin, and then it's going to become unitless, which is kind of necessary because B is a natural log and Y is a natural log. And that's going to give us the activation energy in joules per mole. And then the only last thing that you need to do is upload your work so that I can see all of the great work that you did. So any spreadsheets that you got, anything that you jotted down and stuff, make sure to upload that so that I can see it. I'm gonna post this notes page here onto Canvas so that you guys can see that as well. And that's pretty much it.